Welcome viewers. In this video we are going to do design of equipment structure using Eurocode. In this we are going to do a 400 kV post insulator support structure. Before going to watch this part 2, which is having a seismic load calculation, slenderness and load combination, and finally the robot model for 400 kV post insulator support structure and the design of a vertical member using robot structure model. Before going to watch this part 2, you can watch our previous video, that is part 1, which used to discuss about the input required for the design of 400 kV post insulator structure, self weight calculation, loads from conductor either in a normal tension and the short circuit forces, wind and snow loads calculations as per European standards. So this you can watch in our part 1 video. The video link for part 1 is given in the description. You can watch before going to watch this part 2. Now let me look into that calculation of seismic loads and followed by slenderness, load combination, robot model and design of a vertical support. So let me start with the seismic loads. In that seismic load, we had considered the seismic coefficient as 0.3. Ground types we can consider as C, and behavioral factor is 3. Type of elastic response spectrum curve we can consider as S2. For seismic values and these kind of input definitions which are given in the EN 1998 part 1, this calculation are well explained in our previous video. The video link also provided in the description. You can watch those in detail. So for the time concerned, we can skip this explained in this video. So you can refer the previous video of seismic load calculation in European standard EN 1998. Only change here is, in that video we had considered the total height as 10 meter for our tentatively. So that is here in this calculation we had considered as actual requirement, which is a 7.3 meter, which is a summation of equipment plus the support structures over that with half of the conductor diameter. And another one change is the total vertical load. In that video about the seismic load calculation, in that we had considered only 10 kilonewton. That is a approximate. In this we had considered the total load as per our calculation in self weight. So this is a summation of equipment plus structure plus weight of conductor. So only these are the two change with respect to that video. So using that method to find the seismic force, we are getting base shear force as 1.77. And second thing is we need to find out the importance factor while it is going to combine with the other loads such as dead load or live load. So for that we need to refer to table 4.1 EN 1998 part 6. So in the right hand side you can see that European standard EN 1998 part 6. In that table 4.1 there are 4 classes, class 1, 2, 3, 4. The class definitions are given here. So in the first category it is minor importance for public safety. Second one is which is not belonging to 1, 3 and 4. The third one is collapse may affect surrounding buildings or areas likely to be crowded with people. Third one is a vital importance type of building. So this is applicable for our equipment support structure, which is like tower kind of structures. So in the note you can see that importance factor gamma I equal to 1, which is associated with the event of seismic. Also in the fourth point it is mentioned as for class 2 we need to consider 1 as an important factor, and followed by the note which is mentioned in the below, which is stating that based upon the important classes 1, 3 and 4, the values for important factors are 0.8, 1.2 and 1.4 respectively. So this is what here we are having. In case of the important class is 2, then the importance factor is 1. So for one important classes, the important factor is 0.8. Similar like for fourth important classes, the important factors for structure is 1.4. So this is as per table 4.1 EN 1998 part 6. So we can consider 3 for our structure design. Next one is a slenderness check. For that slenderness check, we need to refer class J6 2.1 of EN 50341 part 1 for limiting slenderness. So here you can find in the right hand side for leg members and chord, the recommended maximum slenderness ratio for leg members and chords shall not exceed 120. So this is what considered here, and actual slenderness ratio, if you want to calculate it, is 1.2 into height divided by I. I is a radius of gyration to the respective axis. So here, as we are having the circular hollow sections, we are selecting this as 219.1 into 8. It is a standard hollow section which already we considered here in our first part video. So that we are considering here. And the member span is nothing but it is a height in millimeters. So finally this value of radius of gyration will be picked from the table according to that section chosen. So there is a table which are listed here. So based upon that, the radius of gyration will be picked from this table and placed here in this cell. So then the actual slenderness is nothing but it is a 1.2. 1.2 why we are considering is this equipment support used to fixed at the base and hinged support at the connection due to the equipment and conductor. It was assumed like a propped cantilever. So it is considered as 1.2. Generally for cantilever structures we need to consider 2. So it's depend upon the designer. We need to fix this factor. So we are considering here 1.2. Sometimes it can be 1.67 or even 1.8 also, or sometimes it can be a 2. As considering it is like a cantilever structure. It's depend upon that, and limited is 120, which we are considered. So that actual divided by limited is nothing but the usage factor. If it is less than 100%, then it can be called as a safe. So thus the slenderness check procedure is get completed. Next we will move on to the modeling of a structure in a robot structural and applying the loads on that. Then later we can discuss about the load combinations. So on the screen you can see that robot structural analysis windows. In that you can click new in the left hand side top. So here we need to select the project as frame 3D, which is in the third icon in the top. So now the window is open. For a multi and complex kind of structure, it is better to create a structural axis. For that we need to click this right side icon in the top. So it is a simple structure which we are going to design as a post insulated support structure. So for this, just we will create a node and then add the members. So click the third icon in the right hand side nodes. So here the first node we can type it here as 0, 0, that is 0x, 0y and 0z. We can also click this node view, like in the bottom there are some icons. So click this so that we can able to find out the node icon here. So next we need to select the structure height node. So for that the height of the support is 4 meter and the height of support and equipment is 7.31. So for this we need to create another 2 nodes. So here X is 0 and Y also 0, only the Z, that is vertical, is going to 4 meter for structure top, and the third should be 7.31 as a equipment top. So these are the three main node we occurred. For view of 3D, we can click this home icon, which is just above the viewer icon. Now we need to add the members. So here in the right hand side, the fourth icon, we need to click it's showing the members. So in that you can see some default sections. So click here, three dots. It will show you the database. When you click this database, it is showing only UK sections, EAC, E and some chorus, something different. But the European database is missing here. So for that we need to go to tools first, then click job preference. Here in the material it is mentioned as British. Change this to European or Eurocode. So steel grade also you can select here. So concrete and aluminum and timber, no need to bother. So click this save current parameters as default. Then go to database. In that steel, here you can see that it is mentioned as UK and some chorus AC. So here we need to click this adding a new database. So here from the drop down list you can select the Eurocode. OK. Then we need to update other things also, like we need to worry about vehicles. Next, coming to the design code, we need to change this to Eurocode. So click here and select from this list. So it is 1992 old code, so we need to select this 2014 with annexer. So for steel connection it is OK. So again save current parameters. So then coming to loads, here it is mentioned as British standard. So we need to select this. Here also we can change to European code. Save current. So that's all. We can close this. So now go to member here in the fourth icon. Now select this 3 dot. Here you can see the Eurocode. So in that, for circular hollow section we need to select this TRON. So the definition also given here, round hollow tubes. So as per our calculation we can consider circular hollow section of 291.1 into 8, but here only up to 6.3 we are having. So here that circular hollow section we consider in our calculation is 319.1 into 8. So this is not available in the robot structure database for Eurocode. So we need to create it. So for that select this parametric, select this tube. Here we can directly enter that 291.1 as outer diameter, and the thickness we know that it is 8 mm. So we can mention here circular hollow section of 219.1 by 8. Also we can give some color indication. Click add. So it is added now. Then again for equipment support structure we can select some round profile which is of diameter 200. So this is some dummy member, we no need to worry about it. If it is a equipment support structure, we can give some different color also, add it. Now from this drop down list we need to select the structural section, draw from first grid to 2 which is a equipment support structure, and from the drop down list you can select the round material. From here to 2 to 3 is a equipment support structure. So you can right click on the window and click the display members section shape. So if you click this mark with colors and select these sections with the legendary, so it will show the color code with the legend here. Now we need to apply the loads as per we calculated. So our load is start from here. We need to identify what are the primary loads. So we can create in the robot structural analysis, go to the loads, load type. Here one you can consider as a dead load, add it, and the second one live load we need to select from here. This may be maintenance or workmanship load. We can add it this also. The third category we can add as a dead load, which is a conductor tension. Add. Fourth one is you can consider as a wind X. X is nothing but parallel to conductor. Label as WX. Fifth case is WY, wind perpendicular to conductor. So any name you can give here. And the sixth one we can add it as a snow load. The label you can give it as SL. You can consider altitude as less than 1000 meter. Next is seventh one we can consider seismic EX. Seismic X. In the eighth case we can consider seismic Y. Okay, it should be seismic cases in the nature. Also this is seventh also we need to change to from snow to seismic cases. We can add it here. Sorry, instead of adding we need to modify this seismic X into. So we need to click this modify so that the snow nature will convert it into seismic. This will help while doing the automated load combination in robot structural analysis. If you are doing like this, then finally we need to give that short circuit forces. So we can give it as SCF. So here conductor tension which we had considered as a dead load, this is without deviation. So we can also mention as tension 0 deviation, modify. Again a new load case we can add it as in the 10th as tension as per deviation. So this is with the deviation. So coming to the 11th case, which is accidental case, short circuit force with the deviation. We can add it here. Also here in the 9th case, short circuit force we had mentioned as a nature. We forgot to change this. So this we need to modify as accidental. Modify. So I hope all the load cases we had added here. So as per this nature of the load case, self-weight we had added, conductor loads, conductor tension with the deviation and without the deviation we had added, and short circuit force we had added with the deviation and without deviation. Wind load also in X and Y direction is added. Seismic snow load also added, and finally the seismic loads X and Y also added. So there are 11 number of primary load types which we had added. Now we can also click here in the bottom left to view the member numbers. So the black text are showing the member number, and the red color text are showing the node number. So it will helpful for us to apply the loads. So now click load table. So for better understanding, we can change this window style horizontal. So here first it is selected self-weight, but self-weight we are not going to apply the both equipment and structure. So part of the structure we need to select here and enter here only the one, that is only on the steel structure we are going to apply the self-weight as per the robot structural consideration or model, or we can directly apply the self-weight as we calculated here. So for self-weight, instead of applying or instead of considering as per the robot structural model, we can also apply as a member force. So here you can select as we already calculated. So we need to apply it in the FZ direction, that is minus. So here 195, which is nearly equal to 2 kN. So we can type minus 2 kN. This is for member load. For equipment, we already calculated it is 350 kg. It is nothing but 3.5 kN. Next one. So here in the member force, once we applied, we need to change this also, because this weight member self-weight will be acting only on the CG, that is the center of gravity. So for that we need to apply here that L X distance as 0.5. So this is applicable for equipment also. We are going to apply only on the middle. So in order to view that load by parallelly while we are applying, we need to click this right click on the windows, select loads, click this load values and the load symbols which is above, and click apply, so that we can able to see the loads which we are entering in the table below. So next, so finally we had applied this. Only one thing missing is that conductor weight in the as per the right hand side Excel calculation. So for the weight of the conductor, it is showing 7.8 kg, which is nearly equal to 0.07 kN. So for converting this, we can also have a calculation backup like converting kg into kilonewton, which is just multiplied with 9.81 acceleration due to gravity, and converting those Newton into kN, we need to divide it by 1000. So 0.0 8 we can consider as a conductor weight, which is to be applied in the node of the equipment. So it is a nodal force. So node number we know is 3 color, which is 3, and here minus 0.8 we need to consider. So before applying to next load case, we need to check this support condition. So we need to apply the support condition as a fixed. So select the node 1 by dragging it and click this icon in the supports. Click it as fixed. So now the structure is having the fixed, because this hollow profile used to transfer the bending moment from the applied forces. So it is better to give the fixed at the base. So now we can apply the next load case, workmanship load, which is a nodal force. We can apply it at the node 2. So it is vertical load. So here you can see in the right hand side for Excel calculation, workmanship load is 1 kN we had considered. So it is -1 downward. Next we need to consider the conductor tension, which is a third load case without deviation. So we need to apply it at the top of the equipment, which is a conductor fixing point. So we need to apply this as a longitudinal force, which is parallel to the conductor span. So node 3 we need to apply the load value of without deviation 0.2 kN. Sometimes this should be calculated along with the wind and ice, but we can consider this only the dead weight of a sag. Next one is we need to apply the load case 4, which is wind parallel to conductor. So here for structure we can apply a uniform load. Structure member is 1, you can see in the screen, and the wind intensity kilonewton per meter is 0.5 in X. So we can apply here 0.5. Next one is in the same load case we need to apply equipment wind. So for that it is a member force we had calculated here in kilonewton, a point load 1.04. So it should be applied in the member number 2 at CG, that is center of gravity for this. So for that we need to apply X equal to 0.5. So you can see in the window it is applied in the mid of the equipment. Wind on conductor is not applicable for this case, because when the conductor span in this X direction, if the wind also flow in the same direction, there won't be any wind impact, because the conductor span is perpendicular to the wind direction. So next case is a transverse wind in Y. So for uniform load for structure we need to consider same as case 4. Only change is here the direction, Py is 0.5 instead of Px. So the second case we are applying here for wind. Next again for equipment it is a member force. As the equipment and structure is remain same in both the direction in size, we can apply the same force value. Only the direction of force is going to change. Again here also we need to apply at the center of the equipment. So X equal to 0.5. And finally we need to apply the conductor wind on conductor also. So for that nodal force is applicable for this. The node is a top node which is in the equipment top. So the value here is described as 0.22. So these are the wind load. Next one we can ignore this diagonal wind for time concern. Next we can go for snow load. The snow load we can apply as a nodal force at node number 2. The snow load value is 0.63, which is in downward. The seventh load case is seismic. Seismic also node force we need to apply at the weaker point. So here the weaker point is connection point of equipment and structure, that is node 2. The seismic value, base shear value we had calculated is 1.7. So we need to enter here 1.77. Next is seismic in y direction. The node remains same. Only the direction is going to change. The magnitude remain 1.77. Next load case is load number 9, short circuit force without conductor deviation. So for that we are having the Excel calculation in the right hand side. So here is a without conductor deviation, we need to apply this parallel to conductor span because it is a flexible conductor. So it is a 6 we are applying in the node number 3. Next load case is conductor tension with deviation. So again this nodal point is 3. So here that f of x, f of y, f of z value are given here. So 0.2, 0.04 and 0.04. Next short circuit force with the deviation. Here you can see f of x, f of y and f of z. So the same thing we are going to apply here. So finally we had applied all the primary load cases. Now we will move on to load combinations. So after completing these primary loads, we can go for load combinations. For that load combinations, we can close this load table and maximize this structure window. Now go to that automatic load combinations. Click here. Click fully automatic combinations. Select here the code to be followed EN1990. So here you can see that the estimated number of combinations. So we need to go into detail about more. So here by default this accidental load and fire load also selected, but in our case as it is a outdoor structure there is no requirement of a fire load test or load combinations. Also deselect this accidental case, and here that accidental if you select means it will consider the short circuit forces. For seismic alone we can consider separately as a load combination because that seismic based upon that important factor, that load combination factor will vary. But this robot structure will consider the standard European standard procedures for load combination in terms of seismic. So we can deselect it and click back. Here you can see it is 82 now. Click OK. We need to see here the load combination. If it is not available, you can just press these calculations. So after that we can able to see all the load combination here. Suppose if you want to delete the load combinations automatic and if you want to give only the manual calculation, go to loads, click automatic combinations, select here none or delete and press OK. Now there is no load combination here listed. So we can test this now. So there are several load combinations which we had defined: ULS, SLS and accidental load cases. So now we need to define the seismic load combination. That we can do it in manual combinations. So there are some, so we can start with the 61 or any number which we record. So this is one dead load plus 1.2 seismic load, because we had considered the seismic load combination factor while calculation is 1.2 here based upon our importance class. So click here. So dead load. So here the point is telling 1.35, that we need to change it as 1 for dead load. And for seismic load case we can consider 1.2. And the same we need to click new here in the left hand side bottom, and this is accidental case. The load combinations you can consider as 1 dead load plus 1.2 seismic Y. Click OK. Again we can add here 1 dead load and seismic Y is 1.2 factor. So you can see here the combinations. Click apply. But in 61 we had given us accidental load case that we need to change. So for that, to close here and go to load types. So here we need to select 61, which is showing as a dead load. Generally it is a seismic case. We need to modify this. Also this, it is showing as wind. We need to modify. After doing all this, we need to click these calculations, which is in the top just below the main bar. So in calculation there is no error. Go to design. Here you need to select this ULS, because that structural member used to design only for ULS cases. The member here number is 1. Click calculation. Now you can see this utilization ratio is 0.37. Here there is some difference in slenderness ratio which we calculated earlier. It is some coming around 64 as per our Excel calculation, but here it is showing 53.56. That it is because in our slenderness ratio calculation we got multiplied with 1.2 the height. If we are going to multiply this 1.2 with this 53.56, then we will get that 64. We can also do it here in this robot structural analysis. We want to save this. For that, go to design, steel member design options, code parameters. We need to select here the column, or we need to create, and we need to type here 1.2, the real length factor, so that we will be getting the both slenderness calculated manually and the robot same. So now we understood that our structure member is pass having the utilization ratio which is 0.37 less than 1 safe. Then we can able to take the results like deflections by clicking the deflection. Deflections we used to take from service load combination. So these are the deflection result. And support reaction also we can take by clicking the results, reactions. So if we want to get for primary load cases, for simple cases, we need to select here. And for SLS, we can select this SLS US. So this is what the final design procedure for 400 kV equipment support structure. Thank you. Look description for more related videos. Subscribe to this channel for more updates. Thank you.